Okay, folks, over this next set of lectures, I would like to discuss anthropogenic climate change. Anthropogenic just means human caused. And in so doing, I do want to acknowledge that there can be some personal beliefs that interact with an understanding of anthropogenic climate change. And I'll remind you, I don't require you to believe what I am going to go over in this course, but I do require you to know what science in general thinks about this. So when you go to answer questions on quizzes, I would like you to answer them based on what science in general, the majority of scientists believe about this subject, which is what I'm going to cover in these lectures. So just a note on this background that I've got on this slide, it's actually a representation of temperature over time. And this is the global average temperature from the year of 1850 to the year 2018. Hard to see in that red there. The scale of variation is about 1.2 Celsius or 2.2 Fahrenheit, so that the coldest blues here are about 1.2 Celsius colder on average than the warmest reds. Over the past 170 or so years, we can see that there has been an increase in temperature, especially over the past 100 or so years. And as we're going to discuss today, the field of climate science is relatively certain that that increase in temperature is largely due to human activity. I'll point out that because this is still an emerging scientific discipline that we're still studying a lot about, that I'm going to have a lot of different sources for you if you would like to check out more things about this. So this source here is just about this background, but be on the lookout for these little boxes if you find yourself interested in any of these concepts or want to look into them, or if you find that you don't believe the things that I'm talking about, if you want to find something to argue with, these are the places that you can go to find material with which to argue. Before we get really into the meat of it, I want to give you the takeaways from this lecture up front, because I think they're important. Earth is warming to what I would consider, and what scientists in general would consider, a dangerous degree. Not dangerous to life itself, but dangerous to human civilization. And it is almost certainly due to human activity. The current changes that we observe are not dominated by natural cycles. Natural cycles do not line up with the warming we've seen. They cannot explain the warming we've seen, especially over the past 100 years. Nor are the current changes to Earth's climate a net benefit to society. I want to point out that climate change, of the scale that we are currently observing, by themselves will not destroy the planet, will not destroy the biosphere. But our current way of life as humans in this civilization that we live in could be irreversibly damaged by things like human migration and conflict resulting from this climate change. That conflict is the only thing which really could destroy humanity and most of the biosphere if we launch all of the nukes. But that is sort of getting outside the realm of climate science, and so we're not going to discuss that part very much at all. It's misleading to say that the science is settled. The science is not settled, nor is it ever. That's the point of science. Science is always open to revision. But not being settled is not the same as having no idea. No science is settled. And you have a right to your own opinion on this, all these topics. But an intellectually honest opinion really should be grounded in empirical, measurable evidence. And if you don't agree with the things that I end up discussing today, you should know why it is that you disagree with them. You should know them well enough to have an informed opinion about why you disagree with them. I will always be happy to answer questions from you on this. If you want to use the email that you have for this course and you want to ask me questions about this in your future, you are welcome to do so, going out beyond the end of this course if you'd like. Without insults typical of the social media discussions that tend to dominate this sort of thing. So we'll break this down into several sub-lectures this time. First, we will focus on the physical principles, and then we will talk about how we actually measure the climate. We will talk about the current changes, and then we'll place them in the context of past climate changes from before humans were having an impact. We'll talk about various fallacies in brief that people tend to use when climate change comes up, misleading ways of saying if this, then that really don't follow from the if statements. We'll talk about what the future effects are likely to be based on modeling that we do to predict those future effects. And then we'll talk very briefly about some solutions, although that is not the focus of this lecture at all. So here are some of the physical principles that we're going to learn about in this sublecture. We will talk about the greenhouse effect. It's a little bit of a review from a past lecture. We'll talk about forcings and feedbacks, which are terms you've heard before, but not rigorously defined. We will talk about rates and magnitudes, things that you have seen also in this course, but maybe not rigorously defined in an abstract sense. And we'll also talk about rates and magnitudes of climate change. We'll mention albedo, we'll mention aerosols, which are a couple of vocabulary words you'll want to know. And then we'll talk about scientific papers as the unit of scientific research, which really isn't a physical principle as much as it is the way in which we get to know what it is that we know in science and how we convey that information to other scientists and other people. So the greenhouse effect. To review what we already have seen about this, some molecules can absorb infrared light based on their vibrations. How they vibrate, and when those vibrations match the frequency of infrared light, those molecules can absorb that infrared light, which is the same as heat radiation. As levels of greenhouse gases increase, Earth warms and emits more radiation until it emits enough radiation to stabilize that temperature. And so that's why as you increase the level of greenhouse gases, you will increase Earth's temperature. So as a reminder, this here is a graph of outgoing radiation from Earth. The red curve is what it would be in the absence of an atmosphere. And then the presence of the atmosphere means that less radiation leaves, especially at certain wavelengths of light, dependent on those greenhouse gases. And that's because those gases are absorbing that radiation before it has a chance to leave Earth's atmosphere. What are feedbacks? We've mentioned these in a couple of different instances, but I want to give you a general sense of what a feedback is. A feedback is when an initial change in any variable has an impact which affects that change, either reinforcing and increasing that original change would be a positive feedback, or partially negating or mitigating that original change, which is a negative feedback. So once again, positive feedbacks, change has effects which reinforce the change. Negative feedbacks, a change has effects which counteract the change. When thinking about climate, a lot of times what we're thinking about is temperature. So a positive feedback would be warming, which causes more warming, or conversely, cooling, which causes more cooling. When we talk about positive or negative feedbacks, the direction matters, right? Warming is not always a positive feedback. It depends on what that initial change was. So warming causes warming, or cooling causes cooling would be a positive feedback. Warming causing cooling, or cooling causing warming would be a negative feedback. Things that are positive feedbacks tend to make climate change worse because they reinforce the direction of change. Whereas negative feedbacks tend to make climate change less bad or stabilize the climate at a particular level because they counteract any changes that go on. Here are two commonly discussed examples that are very important. So if we warm the climate, it increases the amount of atmospheric water vapor in the atmosphere. Water vapor is a greenhouse gas. That means increased greenhouse trapping of radiation, which causes more warming. And you can see where this goes. More warming means even more water vapor, means more trapping, means more warming. And so positive feedbacks end up in this sort of upward spiral or downward spiral, depending on which way is up and down and which way the initial change happened. In contrast, here's a negative feedback that can happen. Climate warming causes that increased evaporation, and if that evaporation condenses into clouds, those clouds can reflect sunlight. And as a result, that causes decreased solar radiation, which causes some cooling. So this would prevent warming from having some runaway effect. That's a negative feedback. Those are two common ones, and we've discussed a couple more, and we'll see a couple more in this lecture. Let's talk about rates and magnitudes. Those are very general terms that refer to, in the case of magnitudes, the total amount of something, total amount of temperature, total amount of distance, total amount of matter, like mass, something like that. Rates are how one of those quantities changes relative to another. Oftentimes, and in the context of climate change, a lot of times those are going to be time rates. So it'll be temperature change per time, per year. But a rate could also refer to something like distance per time, right? That's a speed. A speed is a type of rate. Going back to earlier in the course, geothermal gradient, which is temperature per distance. So the change in temperatures go down into Earth's interior. That geothermal gradient is a rate. Thing in common mathematically that you see is one is divided by another one. It's relative to that change. Oftentimes, a word that will indicate that we're talking about a rate is per, right? Miles per hour. If you see per, that means division. That means we're probably talking about a rate. Now let's talk about the rate of climate change. And here we're looking at about the last 20,000 years, right? So this is 20,000 BC. Here's 0 AD. Here we are in 2020 or so. What is it? When I'm speaking right now, it's 2022, but you might be watching this a little bit later. Hopefully you're not watching this earlier or something has gone wrong. At any rate, we can see what the temperature is over the last 20,000 or so years. About 20,000 years ago, it was much colder here. So the magnitude of temperature was much lower than it is today. And the total magnitude of climate change coming out of the last ice age up to before humans had an impact, right? So this amount is much greater than the current change. So this is since the ice age. And this is current change. So, right, the magnitude of that change was larger coming out of the last ice age than the changes that have happened recently. It's the total amount. However, the current rate of change, the slope of these lines, or the rate at which climate is changing, is much more rapid and severe now than any point coming out of the last ice age. So you can look at that based on the steepness. The steepness of the curve here is almost vertical. It's very steep right now. The rate of climate change is very high right now. Whereas looking over the past 20,000 years, even coming out of the last ice age, it was never that steep. The change was never that rapid. The rate was never that high. And that being said, the magnitude of warming could exceed the warming coming out of the last ice age by 2100, especially if we don't do any changes. So our total change by 2100 could be as large as that, which would match the changes coming out of the last ice age, and then it could continue to shoot up after that, depending on what actions we take. So what do I want you to remember here? I want you to remember what magnitudes and rates are. And I want you to remember this. The magnitude of change that we've observed over the past 100 years is small relative to the change in the ice age, but the rate of change is much greater. Let's bring up a vocab word called albedo. Albedo really just means reflectivity, how much light a surface can reflect. So a surface with high albedo reflects a lot of light. These tend to be brightly colored. White things tend to reflect a lot of light. Black things tend to absorb a lot of light. They have a low albedo. And so we can just describe that in terms of a percentage. So something with an 80% albedo reflects 80% of incoming light. 10% albedo reflects 10% of incoming light. And here over here, you see a diagram of several things like clouds and snow having high albedo, forest and water having very low albedo. Asphalt would have an albedo of almost 0%. right? These are important because albedo ends up being a key part of climate change. Often it is involved in those feedbacks that we talked about. Right? So, for example, if you have a lot of ice in an ice sheet and it's got a high albedo, but if you start to melt it, suddenly you're covered with ground surface, which is going to have a much lower albedo. It's going to be much darker. It's going to absorb more light. So that means as warming increases and your ice melts, you have a lower albedo and you get even more warming. So that's a positive feedback. It's a pretty common positive feedback that we see both in terms of warming and in terms of cooling. Clouds have a high albedo. Is that going to increase or decrease with warming? That depends on what time of day. It depends on all sorts of things. Clouds end up being pretty complicated. We won't worry too much about them, but know that they're involved here. Let's talk about aerosols too. Aerosols, sol meaning solution, meaning dissolved, sort of, but it's dissolved in air. Particles so small that they can be suspended in air are considered aerosols. What are some examples? So dust in the air could come from volcanic ash, could involve pollen from different plants, could even be sea salt from sea spray going up, leaving some of those salt crystals behind in the air. They're small enough to be suspended in the air. Soot from burning things. All of these are considered aerosols. Why do we care? Because aerosols scatter and help reflect some of that light, so they generally cause cooling. If you increase the amount of aerosols, you cause some cooling. So that has an influence on climate that we'll see. Lastly, scientific papers are the unit of scientific production, are the means by which scientists convey information that they've studied. And so this is a paper that I've put out, not really directly related, tangentially related to climate change, but I wanted to show you what one of these looks like. And I wanted to point out that these papers are subject to what we call the peer review process. That means that other scientists read these papers before they're ever published for general reading. And those papers are often, almost all the time, other scientists come back and say, you need to change this or that about your paper, or consider this other influence, yada, yada, yada. But they can also just be outright rejected if the methods, results, or conclusions do not stand up to scrutiny. And here you see some examples of what some of those peer review comments can look like. They're usually not just, fix some formatting and you're done. They tend to be very specific and important things that scientists need to look at to advance the research. So you can see they can be pretty brutal, and you can end up nearly having your paper rejected or having your paper rejected until you fix some of these comments. I point this out just to say that, scientists are not just throwing their results out there without anybody looking at them and scrutinizing them. They get scrutinized by this peer review process, and that helps weed out the bad science and leave only the good science behind.